and thanks a lot for the opportunity to share some of my work here. So I'm going to be talking about mentalization, which I define here as the ability, broadly as the ability to correctly infer others' beliefs, desires, and emotions. And I assume everyone here is well aware how historically the investigation of mentalization is heavily intertwined with the investigation of autism. And while there's been a lot of work looking at potential mentalization deficits in autistic people, there's still quite some open questions and challenges. Maybe first and foremost, many of the classical tasks that have been developed to assess mentalization and are still widely used these days typically show ceiling effects by early adulthood, meaning that they lack sensitivity for mentalization difficulties in adult autistic people. And probably somewhat relatedly, our understanding of the underlying cognitive and neural mechanisms is also still fairly limited. So, for example, there's little convergence about what brain areas might be implicated in autism. And also some seminal findings recently failed to replicate in larger samples. And so there are several possible reasons that might be driving this. One reason we already heard in both previous talks about is that many of these established tasks lack true interactive components in contrast to real-world mentalization. And another reason might be that analyses are typically concerned with analyzing observable features that are indicative of underlying mentalization rather than trying to get at the underlying processes directly. And I hope it will get clearer in a second what exactly I mean by that. And so an alternative approach that some people have been proposing relies on a combination of two ingredients. First, using simple interactive strategic games like rock, paper, scissors, where the only way to win above chance is precisely getting inside the other person's head and predicting what they will play next. And then combining this with a cognitive computational model that captures the underlying reasoning process. So if you're less familiar with computational modeling, the idea here is that rather than directly analyzing behavior, to formalize mathematically the putative cognitive processes and how they develop from trial to trial. So now pointer is not working anymore. There we go. How these cognitive processes develop in a way that can explain the observed sequence of actions. And typically these models then have a small numbers of parameters that allow tailoring those predictions to a particular participant. And so what could such mentalization or strategizing look like in rock, paper, scissors? Well, in the simplest case, I could not think much about the other person and just have a tendency to repeat what I did in the past. So if I play paper, I might just play it again. Or I could try to learn about the other player's future behavior based on their past behavior. So Lisa here might predict that Bart will play paper again and play scissors instead. Or I could go a step further and try to learn what you are learning about my future behavior based on my past behavior, and so on. And so there's a series of increasingly complex strategies that people could be using in this game. And the key question then becomes, which of those strategies is the other person using? And so building on previous work, we recently introduced a model that captures what might be going on inside people's head while they're doing this in rock, paper, scissors. And I'm not going into details here, but the main idea is that people hold beliefs about potential strategies that the other person might be using and update those beliefs if the observed behavior is in line with the corresponding strategy. And crucially, how much they do so is regulated by one such subject-specific parameter that governs their sensitivity to others' reasoning processes. So in other words, that captures how adept one is at recognizing latent strategies from observing behavior. So in recent work that is currently under review, we extensively validated this approach. And amongst other things, what we did is we programmed and carefully calibrated artificial opponents excuse me, that implement these different strategies that I just sketched out, giving us an objective measure as to if and how quickly participants can adapt to these different ways of reasoning of the opponent. And in a large student population sample, we do find that almost everyone adapts to different strategies, And most people can do so, again, even against fairly sophisticated high-level strategies, given enough time. Now, this approach also allows us to ask if some of the cognitive process variables that the model predicts from trial to trial are encoded in a brain when looking at a subset of participants that did play the game in the scanner. And here we were particularly interested in the extent to which participants revise what they think about the other's reasoning process according to our model. And indeed, we did find that this was linked to activation in key hubs of the social brain network, in particular the right TPJ and the bilateral anterior insula. And we could even turn this around and training a machine learning algorithm on a subset of participants, predicting completely independent, unseen participants, how much they were updating those beliefs at a given point in time. And this worked very robustly and very consistently across participants, suggesting that the underlying neural activation pattern is highly generalizable and can be seen as some kind of neural fingerprint of neurotypical mentalization. And so with that, we then asked if we can use this approach to try to better understand what might be going on with mentalization difficulties in autistic people. So we collected a fairly large fMRI sample of almost 100 adult participants. And we hypothesized that we would see a reduction in the sensitivity parameter that captures how good one can recognize strategies from observing behavior, along with the second mechanism that I'm skipping here. And then on a neural level, we hypothesized that we would see changes in the way that these belief updates are encoded, either in a very localized fashion, which would show up in conventional univariate analysis, and or possibly in a rather distributed idiosyncratic fashion, which might not show up in univariate analysis, but which would lead to a higher decoding error when using these pre-trained neural fingerprints to predict belief updates in our new sample. And so very briefly, what we find is on a cognitive level, we do see this decrease in one's sensitivity to learning about others' latent strategies from observing their behavior with higher autistic traits, meaning that autistic participants need a bit more evidence and more time to arrive at the same conclusion about what the strategy of the other person is. And on a neural level, we did not find evidence for localized univariate changes, but we do confirm evidence for distributed changes, as when using our neural fingerprint from the previous study to predict belief updates of our new participants, we do find that the decoding error increases with higher autistic traits. And so in sum, I told you about a new approach to assessing mentalization that relies on a simple interactive game in combination with a novel cognitive computational model that captures the reasoning process while people are learning about others' reasoning processes, and how this allowed us to reveal two effects in autistic adult participants. First, a reduced sensitivity to learning about other strategies, and neurally distributed rather than localized changes in the way these beliefs updates are represented in the brain. Thank you very much.